Okay, hi troops. My name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp Lecture 5, where we're going to be talking about relative risks and odds ratios. So the goal of today is to talk about some relative measures like the odds ratio and the relative risk. And there's many reasons why you might want to consider a odds ratio or a relative measure rather than an absolute measure like a risk difference. So as an example, if you're considering comparing an event that's somewhat rare, so say for example if you're interested in whether or not some environmental effect causes a fairly rare disease, where you're comparing a small proportion of people who contract the disease among the unexposed group and a small proportion of people who contract the disease among the exposed group. And so it might be interesting to know that even though the absolute difference in rates is very small, the relative difference might be very large. So frequently we're interested in relative differences rather than absolute differences. And two particular in the case of proportions that are interesting are A, dividing the two proportions, that's the relative risk, and B, dividing the two associated odds, which is called the odds ratio for obvious reasons. Okay, so let's put some context on this where we use a data set similar to or exactly the same as we've used before. So consider a randomized trial where 40 subjects were randomized 20 each to two drugs with the same active ingredient but say different expedients. So one's a capsule and one's a tablet or something like that, let's say. So consider counting the number of subjects having side effects for each drug. So drug A had 11 people with side effects, 9 with none, 20 total. Drug B had 5 people with side effects, 15 with none, and 20 total, which left 16 total people with side effects, 14 with none, and 40 total. And the interest is whether drug A has a statistically higher percentage of side effects than drug B, accounting for what would be expected by chance. So let's look into that. So there's several ways to approach this problem. In fact, the 2-by table is a surprisingly complex set of 4 numbers, but we're going to approach it from the following way. We're going to assume that the count of the number of people with side effects from group 1 is binomial, with n1 equal to 20 and p1 a proportion that we'd like to know, and y, the proportion of the count of people with side effects from drug B, will also be binomial, with number of subjects n2, which is 20 in this case, and p2 being the proportion of people with side effects from that group. The obvious estimate of p1 is p1 hat, which is x over n1, and the obvious estimate of p2 hat is y over n2, of course. So we're going to use the following notation below in addition to the x and y notation. So x is the count for drug A, y is the count for drug B, and so on. But we'll also, given that it's a little 2-by-2 matrix, we can index the elements by I and j. So n11 is the upper left-hand cell, n21 is the lower left-hand cell, and so on. And then if we need a margin, a point that's fixed by the a point that aggregates over either rows or columns, we'll mark that with a plus. So n plus 1 means that we summed over the two first indices, and 1 plus would mean we summed over the two latter indices. Okay, so last time we considered absolute changes in proportions. But what about relative changes? And as I said, relative changes are often of interest. For example, when the proportions are small, you might have, in the example we were discussing earlier, a 10-fold change in the exposed group contracting the disease over the control group or the non-exposed group, but the absolute difference be quite very small, less than a fraction of 1%. And in that case, it's very natural to consider relative amounts rather than absolute amounts. Well, the most obvious thing to do in the case of proportions is to define the relative risk, which is simply just one of the proportions divided by the other. And then, of course, it doesn't matter which one you put in the numerator and which one you put in the denominator, as long as you remember what you did. So, and just to remind you, so we have P1 and P2 population parameters defined here because remember on the previous slide we actually talked about a model where our data, our IID draws from a population. There's other ways to think about this problem, but that's how we're going to think about it. Okay, so the obvious estimator of the relative risk is the estimated relative risk, which is P1 hat divided by P2 hat, which is of course just x over n1 divided by y over n2. So the relative risk is obviously, there's an issue if y has 0 counts, right? You're dividing by 0. So that's potentially a problem. But also, if we want to create an asymptotic confidence interval where we treat our data, our estimator as if it's normal, there's a problem that this is, of course, bounded from below by 0. And it turns out that the log relative risk, the log estimated relative risk, has much better asymptotic behavior, and the confidence interval looks a little bit better. So what people do is they say, okay, and often when you're working with ratios, we know already that it's very convenient to look at logs. So the log relative risk is just the log of this quantity here, x over n1, y over n2. And that quantity has an asymptotic standard error that you can calculate. And in fact, in one of the next lectures, one of the next 2 lectures or so, we'll show you exactly how to get this standard error. That standard error works out to be 1 minus P1 over P1 n1 plus 1 minus P2 over P2 n2, all raised to the 1/2 power. And that's the standard error of the log relative risk. So what you do to create a confidence interval for the relative risk is you log the estimated relative risk, you add and subtract a standard normal quantile, and then you multiply that standard normal quantile times this standard error of the log relative risk. That will give you a confidence interval for the log relative risk, and if you then want a confidence interval for the relative risk, you then exponentiate the endpoints. Okay, so we could equivalently take the ratio of odds instead of the ratio of probabilities if you prefer. There's a variety of reasons to do that, but one is maybe what if you just prefer to interpret things in terms of odds rather than probabilities anyway. Some people like to think about things in terms of odds, saying an odds of, say, 10 to 1 is more interpretable to them than saying a probability of 10/11ths. So the odds ratio, the population odds ratio, would just be P1 over 1 minus P1 divided by P2 over 1 minus P2. So the odds associated with probability 1 divided by the odds associated with probability 2. So this would be the ratio of the odds of contracting side effects comparing drug A to drug B. And of course, just like the relative risk, you'll be comparing the odds ratio to 1. If it's bigger than 1, it's going to suggest a greater propensity of side effects for drug A, and if it's less than 1, it's going to suggest a smaller propensity for side effects of drug A. And then, of course, the obvious estimate of the odds ratio is P1 hat divided by 1 minus P1 hat, P2 hat divided by 1 minus P2 hat. And you can plug in the x in n1 and y in n2 into that formula, and what you'll find is that it works out to be, if we go to our other notation where we talk about the cell counts, the n11 n22 times n21 times n12. And the easy way to remember that is its so-called cross-product ratio. So the product along the, let's see, when I'm recording, it's not, the product along that diagonal divided by the product along this other diagonal. And so that way you can always remember how to do it. Some people tend to, if you label the elements of the 2x2 table A, B, C, D, some people tend to remember it in terms of the specific letters, but I think it's probably better to remember it in terms of it's the product along one diagonal divided by the product along the other diagonal, the off diagonal. So just like for the relative risk, the odds ratio, the estimated odds ratio, has better asymptotic Gaussian behavior if you log it. So we can calculate a standard error for the log odds ratio that works out to be an incredibly convenient formula. It's the square root of 1 over all the cell counts added up. So 1 over n11 plus 1 over n12 plus 1 over n21 plus 1 over n22, square root of the whole thing. So you shouldn't forget the standard error of the log odds ratio because it's super easy. So again, to create a confidence interval for the population odds ratio, you calculate the odds ratio, log it, calculate the standard error of the log odds ratio, add or subtract a standard normal quantile, say 1.96 if you want a 95% confidence interval, to your log odds ratio, and that will give you an interval estimate for the log odds ratio. Exponentiate the endpoints, and that gives you an interval estimate for the odds ratio. Now, again, we have a little bit of a problem if n12 or n21 is 0, and there's some fixes for that, often involving adding small amounts to every cell is a common fix. Okay, so some comments about the odds ratio. So one interesting fact is if you transpose, so the little 2x2 table is a matrix. If you transpose the matrix, so simply record it, in this case, we had side effects versus none labeled on the columns, I believe, and drug A versus drug B labeled along the rows. But what if we correctly entered in the data with side effects entered along the rows and drug A versus B entered along the columns, and then calculated an odds ratio? Well, you'll get identically the same number. So the odds ratio doesn't care what is the sort of predictor and what is the response. You get the same exact answer. And for both the odds ratio and the relative risk, taking logs helps with the adherence to the error rate. So again, because it's asymptotics, you don't necessarily, if you want a 95% confidence interval, you don't exactly get a 95% confidence interval because it's all based on the central limit theorem. It's only true in the limit. So the taking logs helps adherence to that error rate. And then the interval is just at log estimate, right? Log odds ratio, log relative risk, plus or minus the appropriate normal quantile, then times the standard error of the estimate. And then exponentiating yields the interval on the natural scale. And I would also add, though logging helps, these intervals still do have some issues. They're better than the risk difference, which I think they're better than the risk difference. But still, there's ways you can improve on these confidence intervals, but they involve a little bit more lengthy calculations, so we won't go over them. These are the quick versions. Okay, so let's go over our example next. Okay, so for the relative risk, our PA hat worked out to be 11 over 20, which is 0.55. PB hat worked out to be 5 over 20, which is 0.25. So the relative risk is 0.55 over 0.25 for just, I think it's probably a good habit to write that we're comparing A over B in the relative risk, just to remind ourselves what order we divided in. That works out to be 2.2. Quite a large difference, quite a large indication of a difference, but is it actually statistically significant? Is it something that would be of interest? That in the sense that it could be more than just a chance association. Okay, so let's calculate the standard error of the log relative risk. Here I plug into the formula, I get 0.44. The interval for the log relative risk is then log 2.2, log of our relative risk, plus or minus 1.96, the standard normal 97.5th quantile, times 0.44. That gives us negative 0.07 to 1.65. We're interested on the log scale in comparing whether or not this interval contains 0, and then if we were to exponentiate it back, the interval for the relative risk is 0.93 to 5.21, which again shows an indication that drug A has a greater propensity for side effects than drug B, but isn't exactly significant because this interval contains 1, and on the log scale the interval contains 0. Of course, because log is a monotonic function. If it contains 0 on the log scale, it will contain 1 on the natural scale, and vice versa. So whether you check for 0 on the log scale or 1 on the unlog scale will always yield the identical answer. Okay, let's go over the odds ratio. The odds ratio for A divided by B, well, let's just do this cross product formula. 11 times 15 divided by 9 times 5. That gives us 3.67. The standard error then is square root 1 over the addition of 1 over the cell counts. That works out to be 0.68. So the interval for the log odds ratio is log 3.67 plus or minus 1.96 times 0.68. That works out to be negative 0.4 to 2.64. The interval for the odds ratio is 0.96 to 14.01. Now, so this is on the natural scale. Okay, and then just to finish off our thinking about this problem, consider the risk difference as well. So the risk difference would be here. I think it's a good idea to put that you're subtracting a minus b there. PA hat minus PB hat. That works out to be 0.30. The standard error of the risk difference is given in this formula here. It works out to be 0.15, and the interval is again given here. There's issues with the risk difference formula as well, and we covered some of that before and showed that you can maybe improve on its performance a little bit by adding 1 to every cell, for example. And that was covered when we in the last lecture, I believe. And then the final thing I wanted to just show were two plots, just to finish some thoughts from the last lecture where we talked about Bayesian analysis. So if you recall, if you look back to the last lecture, what we did was we postulated a prior for P1 and P2 that were independent beta priors. We found that if we did that, then we got independent beta posteriors for P1 and P2. We saw that an efficient way to explore the posterior was to do a simulation from it, and that would allow us to calculate things like the posterior mean, the posterior variance, and so on. So if you go back to that lecture, you'll hopefully be reminded of exactly what we did. When you conduct these posterior simulations, you get a PA and a PB, P1 and P2. You get lots and lots of pairs of those things that represent draws from the posterior distribution. And it's convenient to do that because it's just a convenient numerical way to investigate the posterior. If you take the arithmetic mean of those posterior draws, right, you would get the posterior mean for PA and the posterior mean for PB. You could get the posterior mean then for the risk difference, the posterior mean for the odds ratio by taking every pair PA and PB and calculating the odds ratio and so on. Well, here what I did is I calculated for every PA-PB pair simulated from the posterior. I then simply plotted a histogram of them. And this is just an approximation of the posterior, where the accuracy of the approximation only depends on how many Monte Carlo samples I elected for the computer to generate. So if I let the computer run for a really long time, I get a near perfect representation of the posterior. So this, in this case, it's the posterior for the risk ratio. So again, I took PA, divided it by PB, right? And then for all of those pairs, I plotted a density estimate, and there's the density. This gives you a lot of information about where the evidence concerning the risk ratio, the relative risk, lies. Here I drew the blue lines for the 95% credible interval, where there's 2.5% above either below the lower blue line and above the upper blue line, and then I put a reference line at 1 in this case. And as we saw when we calculated the confidence interval, the lower endpoint is just below 1, so that if you were sort of interested in something like significance, you wouldn't get significance. But I think the posterior displays a lot of information and does a lot, gives you a lot more than just a confidence interval or the result of a hypothesis test, or just even worse, giving the asterisks on how significant the p-value is, which some software does. Okay. And then on the next slide, what I'm showing here is the same exact calculation done for the odds ratio. So this is just to give you a flavor of what the sort of output or the desired output from simple Bayesian analysis would be. The posterior is the quantity that you would use to investigate the relative proportions, either through the odds ratio or through the relative risk.